Welcome back to Dr. Liu's VCE Chemistry channel. Today, we are breaking down the equilibrium and rate of reaction from the 2018 VCE Chemistry exam. As I go through this, please feel free to correct me if you find any mistakes. All feedback from teachers, parents, and students is greatly appreciated. In the provided energy profiles, the dashed line corresponds to the catalyzed reaction and exhibits a lower activation energy. The enthalpy change for this catalyzed process is -50. In contrast, the solid line represents the uncatalyzed reaction, which has a higher activation energy of +90. The shift in the gas profile from higher to lower kinetic energy indicates a decrease in the gas's average kinetic energy. This directly corresponds to a decrease in temperature, as temperature is a measure of average kinetic energy. A lower temperature reduces the average speed of the particles, which in turn decreases the collision frequency. Therefore, based on these principles, option A is the only correct choice, while B, C, and D are incorrect. According to Le Chatelier's principle, a system at chemical equilibrium will respond to a change by shifting in a direction that partially offsets the effect of the change. A decrease in temperature, for instance, will cause the equilibrium to shift towards the exothermic reaction, as this process releases heat to counteract the cooling. Similarly, an increase in pressure will cause the equilibrium to shift to the side with the smaller number of gaseous particles, as this change reduces the pressure and partially relieves the stress on the system. The equilibrium constant of the backward reaction is the reciprocal of that for the forward reaction. If a reaction is multiplied by a coefficient, the new equilibrium constant is raised to the power of that coefficient. By combining these rules, first applying the coefficient and then the reciprocal, and substituting the original value, the new equilibrium constant can be calculated. Increasing the temperature will increase the rate of oxygen production. This is because a temperature increase raises the average kinetic energy of hydrogen peroxide molecules, leading to more frequent collisions. These collisions are more likely to have energy exceeding the activation energy, resulting in a higher rate of successful collisions that produce oxygen. Manganese dioxide is indeed a catalyst. It increases the reaction rate by providing an alternative reaction pathway with a lower activation energy, and it is not consumed in the process. A 10-volume hydrogen peroxide solution yields 10 liters of oxygen gas from every 1 liter of solution at standard conditions. The concentration of the solution is calculated through a 3-step process. Convert the 10 liters of oxygen gas to its molar equivalent. Use stoichiometry to determine the corresponding moles of hydrogen peroxide. Convert the moles of hydrogen peroxide into grams and, subsequently, into a concentration in grams per liter. To find the decomposition rate of hydrogen peroxide, set up the experiment with these variables: controlled, temperature, and initial concentration of hydrogen peroxide. Independent, time, dependent, volume of oxygen gas produced or concentration of hydrogen peroxide. Methods measure the dependent variable over time by either collecting and measuring the oxygen gas with a gas syringe, using redox titration to measure the remaining hydrogen peroxide concentration. The color change of the gas mixture conveniently reveals the effect of temperature on the equilibrium between brown nitrogen dioxide and colorless dinitrogen tetroxide. When placed in hot water, the increased temperature shifts the equilibrium to the left, favoring the endothermic decomposition of MnO₂. As a result, the concentration of the brown nitrogen dioxide gas increases, causing the mixture to darken. At time t1, the reaction reaches equilibrium. We calculate the equilibrium constant by substituting the equilibrium concentration values into the appropriate expression. Remember to include the correct units for the equilibrium constant. When the volume of a gaseous system at equilibrium is halved, the concentration of all gases is doubled. According to Le Chatelier's principle, the system will then shift to the side with fewer gas particles to counteract the increase in pressure. In the equilibrium, there are 2 moles of gas on the reactant side and 1 mole of gas on the product side. Since the product side has fewer moles of gas, the equilibrium will shift to the right, toward the formation of dinitrogen tetroxide. This section, Equilibrium and Rate of Reaction, covers 21 marks and contributes to 17.5% of the total 120 marks. Multiple choice questions, 4 marks, Q13. Catalysts lower activation energy to speed up reactions, without changing the enthalpy change. Q20. Lowering the temperature shifts a gas's kinetic energy curve, reducing particle speed and collisions. Q24. Equilibrium shifts to oppose change. Lower temperature favors the exothermic reaction, higher pressure favors fewer moles of gas. Q27. Reversing a reaction inverts its constant. Scaling it raises the constant to that power. Short answer questions, 17 marks, Q2. Higher temperature increases reaction rate. MnO is a catalyst that lowers activation energy. The concentration of a 10 volume H₂O solution is calculated as 27.4 gl, Q7. Heating the MnO₂, H₂O₄ system increases brown MnO₂. Halving the volume shifts the equilibrium to favor colorless H₂O₄ to reduce pressure. If you need my help, please add me on WeChat or WhatsApp and send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.